Hi, everybody. This is a recorded version of the Introduction to Weather lesson that has been done in class. So if you missed the day or want to look back at this, or if you need extra time to finish the notes that go with this lesson, please continue. You may feel free to pause the video and rewind at any time that you need to so that you can go at your own pace. So this is our Introduction to Weather lesson. We're going to be interpreting basic weather data to identify patterns in air mass interactions and the relationship of those patterns to local weather. In other words, we're going to look at some basic data and be able to read some of the things on a weather map to predict, understand, and explain why we get certain weather. For today, we're going to be focused on vocabulary, some of the basic concepts, and an overview of the important weather terms and concepts. As you go through this lesson, in class, you've been asked to take some notes. I'm going to show you what that document looks like. It's available in Schoology. Here you can see what the notes look like in Microsoft Word. If you prefer to take handwritten notes, if that's better for you, you also have that option. These are meant to help you. Use the notes as we go through the unit so that you have access to some information that can help you. So as we go through, you'll notice the words on the left, the terms, and the notes in the middle and the right. So we're about to get to a slide on weather and climate. When we get to that slide in the middle, you'll type in some of the information on the slide. I've provided you with some of the pictures on the PowerPoint, and some of the notes are fill in the blank. Others are you complete yourself, so you can kind of see that it is a guided note structure where some is provided for you and other information you have to provide. So as you scroll down here, you can get a preview for what it looks like. All right, let's get to the lesson. To start this lesson, I'm going to ask you, what weather words can you think of? Take a look at the map for a moment and think to yourself, what terms do you hear on TV or the radio when you hear a weather report? You probably recognize some of these symbols. You may hear words such as cold front, warm front, pressure, temperature, cold, hot, rainy, snowy, windy, and any other terms you may think of that you've heard on the forecast. We're going to go through a lot of these terms in detail throughout this unit. I'm going to ask you, what do you think is the difference between weather and climate? You may pause the video now if you want to think about that on your own. Weather and climate are two different things. Weather is what's happening at a specific time and place, as in right now. So if I were to say to you, the weather in Lynn today is, I'm looking outside, partly sunny, about 24 degrees out. That's happening right now in Lynn, Massachusetts. If it's rainy right now, if it's windy, all of those things that are temporary conditions in a specific or particular time and place is weather. Climate, on the other hand, is the average weather conditions over a long period of time. An example of climate would be, the climate in Lynn is that we have very cold winters and very warm summers, and our spring and fall is moderate. It's predictable over a period of 20, 30 years, sometimes even more. So again, weather is happening right now in a specific time and place. Climate is a region over a long period of time. You may want to pause the video now so you can fill out the first section of your notes. Here's what the notes look like all completed. So throughout this video, now that I've shown you an example, I'm just going to stick to the PowerPoint, but you can pause at the slides if you need to have your notes open and use them. This is an example of how I took the information that was in the PowerPoint and I put it into the document that's going to be used for your notes, like so. Throughout the rest of this unit, we're going to be focused on the weather aspect of this. We'll do climate much later or after this unit. So I'm going to go through some very important words and concepts throughout this just to get the notes done and familiarize you with some of the really important themes that will come up that you need to know. Starting with density. Density is something that has come up constantly throughout the year. We started talking about density in Unit 1 with materials, how compact atoms are in a given area. We talked about how crowded the molecules are. So if you have a sample size of brick and foam, if they're the same size, that brick is going to be a lot heavier because it has more atoms in it. Density is also important when we talked about convection in the mantle with our earth science unit. Convection in the mantle is where things move from an area of higher density to an area of lower density. These same patterns happen when we talk about weather and specifically air. It's a really important concept with weather. We're going to get into something called air masses soon. What happens is cold air sinks and warmer air rises. Whatever is more dense will move down. Whatever is less dense will move up. That happens in the air above us. We have a very large atmosphere above us on planet Earth at any given time. What happens up there is what determines our weather conditions down where we are. And density is a really important part of that. So cold air behaves a little bit differently than warm air, and we're going to get into that as we move forward. You may want to pause now to take your density notes. One of the first words that may have popped into your mind when we talk about weather, when I showed you that map in the beginning, is temperature. It's one of the most relevant terms when you think about how weather relates to your life. When you think about how to get dressed in the morning to go out or do something, you're going to first know, is it warm or cold? What kind of clothing do I need? Temperature is a measurement of how fast particles move, how fast molecules move. The more energy something has, the warmer it is, the more those molecules move, like we talked about with our heat transfer unit. The colder something is, the less movement there is. We use a thermometer to measure it, shown on the right, and it's measured in degrees Celsius or degrees Fahrenheit. Although here in the United States, you're familiar with Fahrenheit, and science will often see the temperature in Celsius. You might want to pause now to do your temperature notes. Precipitation is likely one of the first things you thought of as well, maybe right along with temperature. Is it going to rain or snow today? So there are 4 different types of precipitation. They are rain, snow, sleet, and hail. We know what rain and snow is, and hail and sleet are a little bit different. Sleet is kind of that in-between, like frozen rain. It's not quite snow, not quite rain, but you can tell that the rain looks thicker. It's very fluid. It's not completely solid, not completely liquid. Hail is when you have chunks of matter falling from the sky, like ice chunks. It can be measured with what we call a rain gauge, pictured on the right here. What determines whether or not the precipitation is rain or snow is the temperature in the air above us. So if it's below freezing point, if you remember from our first unit, freezing point, melting point, boiling point, if the precipitation in the air, in the atmosphere, is below the freezing point, which is 32 degrees Fahrenheit, it would be snow. If it is above that, it would be rain. And then there are a couple other things that can happen in the atmosphere that determine whether or not it becomes sleet or hail. In a moment, I'm going to show a video to you that helps explain the precipitation. The video can also be found in the Schoology folder.
Oftentimes in storms, we can get snow to rain, we can get snow to sleet, snow, sleet to freezing rain. But what determines these precipitation patterns? So let's talk a little bit about this. First of all, when you think about the troposphere, which is where the game is played, you're looking at about 40,000 feet. So we're only going to need about 15,000 feet of that atmosphere to A, grow the snow and produce these different precipitation types. And sometimes you don't even need all that. But let's just start up here where the snow crystals are developing. You know, we call this the dendritic growth region. Now, it's pretty easy to produce snow when you've got the snowflakes that are already being produced up there, and they fall down through the atmosphere all the way to the ground as snow, because the whole column itself is below 32 Fahrenheit or 0 Celsius. And so what you wind up with? This beautiful Courier and Ives postcard down here, right? That's easy. But what happens when you start introducing a warm layer? So on average, let's play with that warm layer somewhere between 5,000 and 10,000 feet. Maybe not all of it. So we've got snow. We've always got snow up there in the wintertime, usually at 15,000 feet on up, okay? So here come those snow crystals rolling on down through that layer. All of a sudden, whoop, it goes above 32 degrees, starts to melt either the entire flake or a little bit of it. But once it starts to fall back into that air that's below 32, it becomes a sleet pellet. So it completely refreezes again. And you can hear the sleet. You can hear it on the rooftops. You can hear it on the street. You can hear it on your car if you're just sitting there. And sleet and snow are typically okay to drive in. But this last precipitation type, all right? So let's play again with the atmosphere. Go up to 15,000. We've got snow down through 10 on average. It melts. It's still melting all the way down to about 2,000 feet. And then on under, that air mass is just cold enough to refreeze whatever's at the surface, but it's very shallow. Now, this can vary anywhere between 200 and 2,000 feet. But the problem is you don't get a chance to refreeze that droplet. It comes down as a liquid, and whenever it hits, it turns to ice. And ice is the worst thing to drive on, especially if you're going too fast. Yeah. Stuff like that can happen. So the rain keeps coming down in the freezing layer. It accumulates on everything, the rooftops, the tree limbs, and you wind up with some big problems in through here. And unfortunately, too, you've got power lines involved in many, many cases where that ice is accumulating on the power lines. Now, between the two poles, if you just take, on average, the weight of a 1/4 inch of ice adds about 500 pounds to those lines. And, yeah, that means power loss and all sorts of problems. So those are precipitation types and basically how they form. Obviously, you can get all of the same precipitation out of one storm. You can get a combination of all three. But that's essentially how the atmosphere works for precipitation types.
Another common term that you hear that we associate with weather is the wind. Wind is the natural movement of air. It's caused by the uneven heating of the earth and the rotation of the earth. Meteorologists measure wind speed and wind direction. And it's also caused by differences in pressure because of that uneven heating of the earth that we talked about with the Earth's tilt in direct sunlight and indirect sunlight. Air also travels from areas of high pressure to low pressure. That's a very important concept as well. The tools that are used to measure wind are a weather vane for direction. You often see them at the tops of buildings such as churches. It'll show what direction the wind is moving in. And what's called an anemometer. Notice the design. There's like cups that actually catch the air. And that actually is used to measure wind speed as well. Next up will be a video helping to describe.
It comes at you as a breeze, as a gust, as a gale, or in the scariest of situations, a hurricane or tornado at speeds up to 400 kilometers an hour. Moving air can be as delightful as it can be frightening. But how does wind happen? Here's a one-sentence answer. Wind is caused by air flowing from an area of high pressure to an area of low pressure. The long answer is that there are a bunch of variables that affect wind formation, speed, and direction, including the sun and the Earth's rotation. But let's back it up a bit. The air that's all around you, it's made up of nitrogen molecules, about 78%, oxygen molecules, about 21%, and water vapor, between 1 and 4%. When we talk about air pressure, we're talking about the amount of force that these molecules exert on a given area. When a mass of air warms, it rises and therefore exerts less pressure on the surface. And especially if that air is moist, that rising air can become unstable and create cloudy, rainy, even stormy conditions. That's why low pressure systems are often associated with bad weather. But that low you see on the weather map is only low in relation to the air around it. There's always a mass of cooler, drier air, usually coming in from a polar region, waiting to rush in, push that low out of the way, and sit right on top of the land. That's a high pressure system, and when it it dominates, clear skies usually come with it. So think of the wind as the atmosphere's eternally futile struggle to find a balance between these two competing systems. Air flows from high pressure to low pressure systems to try to reach equilibrium, and in doing so, creates wind. The closer the high and low pressure areas are to each other, the stronger the wind. Now, unsurprisingly, the sun plays a big part in all of this, as it heats the surface of the Earth. About 2% of all the sun's energy that reaches our planet is eventually converted into wind energy, a small portion which we humans tried to harness. The spin of our planet also plays an important role. If the Earth didn't rotate, global winds would pretty much blow in straight lines with cold air flowing from the poles, heating up at the equator and then going back again. But the Earth's rotation produces a force on everything that's moving relative to the Earth, including air masses, a phenomenon known as the Coriolis effect. That rotation deflects the direction of the winds, to the right in the northern hemisphere and to the left in the southern hemisphere. Put it together, and these forces can do amazing things. According to most sources, the highest surface wind speed ever recorded was at the top of Mount Washington in New Hampshire. Wind gusts during a particularly brutal storm in 1934 topped out at 372 kilometers per hour. But in 1996, instruments about 10 meters above the surface recorded winds of 408 kilometers per hour during Cyclone Olivia off the coast of Australia. If it's all the same to you, I'll just take my gentle fall breeze. Thank you very much. And thank you to all of our viewers, especially our subbable subscribers, for continuing to support SciShow, shot here in the Keith Chim studio. If you have a question or a comment or just a good idea, you can contact us on Facebook or Twitter or down in the comments below. And don't forget to go to youtube.com/SciShow and subscribe.
In the last couple slides and the previous video, you've seen and heard the term air pressure mentioned a lot. We're going to go through this quite a bit throughout the unit. It is very important. And you notice that, or you heard that, air travels from areas of high pressure to low pressure. So what is air pressure? Air pressure is the weight of the air above you. So if you're standing on the ground, there's a whole column of air from you all the way up to the edge of the Earth, at the end of the Earth's atmosphere, I should say. And that air actually puts pressure on what's below it. So there are huge air masses that are exerting so much pressure. And when they move around and interact with each other, it gives us our weather patterns. There are what we consider high pressure and low pressure, measured with the device you see on the bottom right, which is called a barometer. We will go into more detail on this, but high pressure brings usually happy weather, which we say H for happy, yay. Fair, not very windy. The sky, you can see the blue sky. It's probably partly cloudy or mostly sunny. Ideal weather. It can happen when it's warm and cold, but when you look outside, it looks nice. When there's low pressure, remember L for lousy weather. It's stormy, very windy, cloudy, overcast, rain, snow, wind, all that stuff that wouldn't want to make us go outside. We wouldn't want to be outside during that. All right, so next in the lesson, we have a short video to describe air pressure.
I know you're not with me every night here, so every night on Fox 9 at this time,
yes,
we like to turn to Scott. He gives a little closer look. Yeah, he teaches us something usually. Actually, for that matter, Scott, a lot of times it's a weather whiz kid who teaches the older folks here something, older.
So what are we going to learn tonight, Scott?
What are we going to learn tonight? Well, some of the basics to weather. What makes nice weather? What makes stormy weather? That's simple, right? Here's the question from Eagle Middle School.
Hi, my name is Jody Gilbertson, and I go to Eagle Middle School. And my weather question is, why is it that high weather pressure is associated with fair winds and clear skies, but low pressure is associated with dark clouds and precipitation?
Great question. So we're talking high pressure and low pressure. She's saying, why is high pressure associated with clear skies and light winds, and low pressure associated with storms and rain? Well, we're going to put it together this way. You have to look at weather as three-dimensional. That's the key here. That was one of the most difficult things when I went to college, when they started talking about the weather in 3 dimensions. I was so used to just staring at weather maps that I'd see in the newspaper here down at the ground. But everything at the ground is occurring by what's happening aloft here. So let's look at the jet stream. This is the jet stream here, and this is high and low pressure here. Now, you have to understand the water cycle, too. Water cycle is as air rises, it will cool and then condense because it encounters lower pressure. So the higher air rises, the pressure goes from high pressure to low pressure. You get less pressure, less temperature. It cools and condenses, makes clouds. So wherever there's rising air, we get precipitation. This is what's happening in the jet stream aloft. Here we'll have a convergence zone aloft here. That's when the jet stream winds are coming together. So as you push the air together, it has nowhere else to go. It can't go up, so it has to go down. And so what happens is we have sinking air, and the air sinks, and it sinks clockwise. So it subsides, as we call it, subsidence. As it's sinking, it warms because it encounters the higher pressure near the ground, and that sinking air also causes a big bubble of high pressure to form here. So sinking air near the high pressure warms and dries, and so you don't have any cloud cover out. We had that pretty much during the day today. As the jet stream's going along, it'll encounter an area where it diverges aloft, and so it separates the air here. We can't have a void. We can't make a vacuum of no air, so something has to replace the air right here, and so air comes up from the ground. So what happens is high pressure now has been over here, so that wind comes out of high pressure, it goes into low pressure counterclockwise, it gets to the middle with nowhere else to go, and it rises to fill this void right here. And so near low pressure we have rising air, and rising air will then cool and condense and make clouds and precipitation. So you basically have rising air causing clouds and rain, while sinking air is generally dry as it warms up. And if you look at high pressure, low pressure on the ground at the surface here, you also have wind that forms between the two. And as I mentioned to the kids, if I take a room and we fill it up with air, we seal it off, and we pump a bunch of air pressure inside the room, then we open the door, the air will rush from high pressure to low pressure outside the door, and because the earth is spinning, it goes around clockwise like this. And so we added a little bit extra here, but generally stormy, not stormy. That's what you got to take away from that, Don.
We don't get quizzed on this, do we?
Oh, yeah. Sitting on your desk.
End of the week, my friend.
All right, we have just 3 more slides. Please keep in mind, I know this is a lot of information at once. Remember, our objective is just to become familiar with some of the important terms. You are not expected to know or remember everything in this presentation. It's just to introduce you to it, and we're going to be spending more time on each of these topics. Next, we are on humidity. You've probably heard the word humid or humidity before. When it is humid out, at least in the summertime, it feels hotter. It's that like really muggy day where you're just going to be like, feel like you're sweating all day. You're going to need an air conditioner if we're in the summer. We have humid days in the winter as well, and that's a little bit different though. It's easier to remember when you associate it with the summertime. So humidity is how much water vapor is in the air. How much water vapor is in the air. If there's high humidity, it's going to feel hotter because there's more matter in the air. There's more water vapor in the air around us and in the atmosphere. And there comes a point where the air can no longer hold the amount of moisture in the air if it's very humid. And that's when it will condense, and you'll see things like fog or dew, or you'll see cars aligned with like a wet substance, which is just moisture, water vapor. Also, you'll reach a point when it's really humid in the summer. Your body needs to sweat to release that, but it has a hard time doing so because there's already the maximum amount of water vapor in the air. So your body struggles to release sweat, and you just feel gross and hot when it's in the summertime. But the bottom line of this is that humidity is the amount of water vapor in the air. We can measure it with a device that's shown here called a hydrometer. And the amount of water vapor that can be held in the air depends on how warm or cold it is. Remember that term density. Warmer air has less density. Colder air has more density, and that affects how much water vapor that can be held. Feel free to pause at this point as well if you need to continue your notes or catch up on your notes. The concept of what air masses are is probably the most important topic to understand with this weather unit. An air mass is a really large body of air that has similar characteristics or properties, such as temperature and humidity. When I say large, I'm not talking large like the size of a large building. I'm talking this covers an entire region of a country or the earth. A huge air mass that affects the weather in an entire region or community or state. We describe air masses with temperature and humidity. It can be any combination of hot, cold, wet, or dry. And we name the air mass based on where it forms. If an air mass originates above water, it's going to be moist or humid. If it originates above land, it's going to be dry. If it originates in a warm part of the earth, like near the equator, it's going to be warm. If it originates in a cooler area, near one of the north or south poles, it's going to be colder. Wherever that air mass forms or originates or comes from, it's going to have the qualities of that area, a region. And then those air masses move. So we are in the northeast of the United States. We can get a dry air mass from central or western United States that moves and brings with it that kind of weather. And when the air masses collide, it makes all sorts of weather changes in the atmosphere which affect us. So we will be going through this. This will be one of the first topics we spend a length of time on in this unit. And we're going to be focused on where the air mass forms and what properties it has and how that translates to weather conditions. Feel free to pause now to complete your notes. You've probably often heard the term front and have seen symbols like that are shown on the slide here on a weather report, or you've heard the term cold front or warm front. So we just talked about air masses, which are huge masses of air that have certain qualities of cold or warm or wet or dry. When two air masses meet or collide, the boundary between them, that's called a front. So when a warm air mass meets a cold air mass, it's like a battle in the air. One of them is going to take over the other one, or not, or they're just going to stay there. No matter what happens, what the result of that battle is, it changes the weather around it in dramatic ways, in drastic ways. So there's always some sort of weather event that is occurring near a front. Warm can meet cold in the warm winds and takes over. Warm can meet cold in the cold winds and moves the warm, or they can be in like a standoff. And regardless of what happens, some sort of weather event happens there. It changes some type of weather condition at these fronts, and they can move as well. We can have a warm front coming in. You may have heard that term on the weather, and that will help a meteorologist, someone who studies the weather, that will help a meteorologist predict what type of weather is coming our way. That's one of the ways they know that we're about to get a storm or something like that. This is another topic we'll get into in more detail and talk about each type of front as we go. But keep in mind, this whole lesson is meant to introduce you to things and let you become familiar with important vocabulary words. All right, at this point, you should have what you need to complete our introduction vocabulary notes. And if you need any help at all, please contact me, and I'll be happy to help.